Hello everybody and welcome back to lecture 4 of the series about the FR theories of the gravity. In today's lecture we're going to talk about the inflation and FR theories of gravity, or in another word we will study the inflationary epoch of the universe in the field of modified gravity, or by describing the gravity by modified theory, which is FR theory. Specifically, we will talk about the Sterpensky model of the FR theories, where in Sterpensky model we have R as a Ricci scalar, as in case of Hilbert Einstein. Actually, by in addition to this term, there is R squared. There is R squared. Let me show you what the main difference for this lecture today. So before I forget, I'll share the screen. So this is the main paper for, not this one. Yeah, this is the main paper for today, comments on Sterpensky model of inflation and its, I will make, believe me, I'm practicing on about the pronunciation of this word, but I will make mistake, I'm sure. So this is the word. I found that this paper, or to talk about, that some kind of new paper is better than taking the Sterpensky, the original paper about Sterpensky model of inflation. Why? Because you know that this model suggested around 1981. From that days until this day, the techniques of the workings, it's different. Techniques of working about the inflation is different, and also the observations and the observables. Now we have more observations and observables, and we can test the inflation in more details. It's 1913, so here in this paper they would took blank data, recent blank data into account. But just I want to mention that in this paper, that will be the blank data 2013, but there is updated data 2018 for the blank. I will try to mention about them and what the difference. It's just about the range for the observables will be different between blank 2013 and blank 2018. And also there is something interesting about this paper, that this paper will show the equivalence between the scalar field inflation and the FR theories of gravity. Just about this point, most of the models of inflation try to describe the inflation, which is, by the way, it's some kind of early accelerated expansion of the universe. The universe at the beginning around 10 to the power negative 36 second of its birth, if we can say that, undergoes an accelerated phase, or accelerated expansion phase. Then when the radiation dominated on the universe, we have that kind of the accelerated expansion of the universe. But what is the mechanism for this early accelerated expansion of the universe? Most of the inflationary models, they use the scalar field as some kind of matter, and the particle of this matter is known as inflaton. Now this inflaton, or this scalar field, has negative pressure, and as a result will produce some kind of accelerated expansion of the universe instead of the accelerated one. In case of Sterpensky model, they will use the modification on the gravity as R plus alpha R squared to produce this accelerated expansion of the universe without any need of the scalar field. In this paper, what's really interesting that they will show that some important models of the scalar field inflation can be produced by the Sterpensky model, or in the inverse case. Okay, actually we have a lot of ground to cover today. I'm not sure if we can finish this one by one lecture, or we need 2 lectures, but let's start just to save your time. And to be clear and to be honest, this is, I read this paper quickly without going deeply in the details and in the calculations. So at any time, if I found that something need some working, I will stop or pause the video, then I will resume it after finding the results. So let's go to the first chapter, Sterpensky model. Sterpensky model, that's m blank r squared, r plus 1 over 6 m squared r. M is just energy scale. Now here let's just relate with our lecture, the first lecture, when we say that's okay, that's S of the metric, and here they are working in the metric formalism. That will be the integral of d for x, the square root of minus g fr. So here it's so clear that's now fr, it will be m blank squared over 2r plus 1 over 12 m squared r squared, because we have this. Now the first point, I remember from the second lecture of our lecture, we said that's transforming or applying the transformation on the action to bring the curvature part of this action from this modified form where we have r and r squared to Einstein form of gravity, or we have a linear term with respect to the Ricci scalar. That will simplify the case. Now, in case of inflation, you cannot compare between the simplicity between the two frames. In Einstein frames, it's really easier than the working within Jordan frame. Why? Because working on inflation requires working on the perturbations. If you want to work on the perturbations with modified gravity, this is really some kind complicated and it needs long calculations. But if we succeeded to convert the action from Jordan frame to Einstein frame with new degrees of freedom, which is scalar degrees of freedom in this case, that will make the thing similar, because this is studied and the perturbation is studied, and we can use the results of that calculation, and no need to repeat the calculation from the beginning. And then when it comes to the observables, we can say now that this is evaluated in Einstein frame, let's relate it to Jordan frame, the original frame, and we can find everything easy and clear. You will understand what I mean step by step, but now just be patient with me. So now we need to convert and to apply the conformal transformation on this action to bring the gravitational part to Einstein form. To do this, let's remember that the first thing that's in Einstein frame, or in Einstein-Herbert action, we have that's R linear term of R, linear first order of Ricci scalar. So we need the first step before doing anything, we should make this one as a linear. Now let me remind you about what the steps in the second lecture. Here in second lecture, we do the following. We have FR, so we add term with FR and subtract term with FR. Why? Because we need here to find R. We need to find R, and then we can convert it to keep this R, but we need at first R to be from the first order. In here, what no need for this step to add RFR and minus RFR. Why? Because if we have clear that we have R squared, so we can say that let's find some term here. Let's define this. This psi as if we define it as psi equals R over 6m, then we can bring this one to this form. How quickly? Because here you have here I'm talking about this one. And let's look at this one. Just instead of psi now put R over 6m, so you have R squared over 6m squared, 6m squared. So we have R squared over 6m squared. Now from here we have a 3, psi squared is R squared over 36m squared. This with this we have a 12, then we have R squared over 6m squared minus R squared over 12m squared. That will be R squared over 12m squared. And this is the 10, because don't forget that here we have this, we'll multiply by this, so it will be 1 over 12. So now we have linear with respect to Ricci scalar. We can write this one as the following. That's we have the integral d for x, the square root of minus g, and we have m blank squared over 2. Then we have 1 plus 1 over 2 m blank squared psi. and we have here r, and then we have minus 3 psi squared. What's the benefit of this? Now remember that when we did or the main idea of the conformal transformation, that the coefficient multiplied by r, I will call it that's omega psi. So here we will define that g mu nu will go to g mu nu tilde as omega squared psi g mu nu. What's this omega squared psi? This will be without 1 over 3. So only this. So it will define, let me use now, it's better to use the blackboard here. So now we define that's omega squared. Yes, omega squared equals 1 plus, let's just be sure, yes, 1 plus 1 over, and here we have 2 over m blank squared psi. Yes, m blank squared over psi. Good. Okay. Now after doing this, let's remember what's happening in conformal transformation. Where we have now let's remember here that after defining this, then we have the square root of minus g will be defined as this, and Ricci scalar also defined by this. And after doing the transformation, we found that we have these terms. Then we said, okay, let's define fr as omega squared, and as a result, we find this term. We have r tilde. This is the final form. We have r tilde. By in addition to this, we have nabla mu len omega, nabla nu len omega. And here we have this form. Then we say that's okay if we define auxiliary scalar field phi as 1 over kappa, the square root of 3 over 2 len fr, and fr it's the omega squared, which they are in our case. So let me here len fr, yes. Now let's go there. If we define that like this, and now fr, let's remember that this is actually fr. Okay. Then we can here, they say that phi will be defined as phi will be defined as 1 over kappa, the square root 3 over n, and then here fr, that's we say that will be 1 plus 2 over m blank squared psi. So psi will be let's say this term 1 plus 2 over m blank squared. That will be exponential of the square root of 2 over 3 phi over m blank squared. That's because of kappa. It's 1 over m blank squared. Then we will say, okay, we need the psi. So psi will be 1 minus exponential of the square root of 2 over 3 phi over m blank squared multiplied by 2 or m blank squared over 2. That will be psi. That will be psi. And as a result, let's remember that as a result here from this, when we define phi as len fr and fr in terms of f, then we can write the action in terms of this auxiliary scalar field as following. But now we have v phi. What's v phi? Is the original term here when we find it over fr squared. But in our work here, we have that fr squared is psi squared. So now we'll hear this term that will be psi squared over f squared, that's 1 minus blah 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 with respect to psi, that's the term which we define it. And if we wrote this one in terms of phi, and this is with in terms of phi, we will find this term here. We'll find this term. And here we have this one. So this is the conformal transformation. Okay, I explained quickly because we did it in the second lecture in details. So now we can see here that we have this equivalent scalar field version of Sterpensky model, where we have here linear. Of course, here there should be tilde, but they cancel tilde. Just keep in your mind that now we are talking about the Einstein frame, not in Jordan frame. And here we have the scalar field, and this is the potential of the scalar field. That's the potential of the scalar field. Now, they mentioned that in case of large scalar field, where this large, so this term will be so small compared to 1. So this term will be so close to 1 because it also they're squared. So v phi will be 3 over 4 m blank squared over m4. It seems like it's cosmological constants or vacuum energy. Now, this term here, it seems that it's a study. Now, this is the benefit of it. That's we know how we can do like this. We can study like these models of perturbations of inflation, because it's just now seems as Einstein-Hilbert action in addition to the scalar field. So this is studied a lot, and many authors study like this. And for this specific situation, we have that ns minus 1 will be negative 2 over n, and r will be 12 over n squared. Now, of course, we'll say what this n is and what's r. The inflation at the big, the inflation, the inflationary epoch produced in the CMB perturbations. And these perturbations, of course, when we want to study it, that there is some specific constraints on this one. The first one is that the ratio between the amplitude of the scalar perturbation to the tensor perturbation should be less than 0.1, and the spectral index, which represents the scalar tilt of the scalar or the power of the scalar perturbation, should be from about 0.96, something like this. So here they mention that note that R has addition 1 over 10 superposition with respect to the scalar field tilt, and those predictions of tiny amount of gravitational waves is therefore consistent with the Planck constraints. The normalization of the CMB and isotropy fix m 10 to the power negative 5. And I forget to mention about n. What's n is the number of E folds, because the inflation, you know, I think it's better to give some summary about the inflation and what the meaning of inflation. Again, I'm talking here about the scalar field inflation. So I will talk about the scalar field inflation and single scalar field inflation, canonical one, perfect one. There is many models about the scalar field, and they are differ one from the other. But let me talk about the simplest case. In the simplest case, if we draw here the potential V phi of the scalar field with the scalar field, just to understand the history of the scalar field, the potential should take this form. Let me mention about what the meaning of this. The scalar field will start with respect to the potential by this here. So here at some point, let's call that this is phi I, the initial value of phi, or at the beginning of the inflation. Now, here at the beginning, the quantum fluctuations will be dominant on the behavior of the scalar field. Then, after some point, the scalar field will start ruling classically. So classical ruling of the scalar field. And I mean by scalar ruling, it means that here the classical behavior will dominate. So we can describe the scalar field classically. And to be able that this scalar field can produce inflationary or accelerated expansion of the universe, it should that the potential should be dominant on the kinetic energy of this scalar field. And this is what's called slow rule approximation. Now, at some point, this slow rule approximation will be broken. So here we have some kind of fast ruling. And when the slow rule of the approximation will be violated, then there is no accelerated expansion of the universe. So we can call this one as f phi f, the value of the scalar field, where the inflation will be the end of inflation. Now, of course, as a result of the inflation, the universe will be expanded a lot. And it means that the temperature of the temperature of the universe will be decreased a lot. And if we follow because the temperature will decrease more and more as the universe evolved and expanded, so it's impossible to reach to the temperature of today. It's 2.7 Kelvin. So how we can avoid this one? Actually, the scalar field here at the bottom or at the minimum of the potential will oscillate or vibrate back and forth and decay. So here we have decay of scalar field. And the decaying of the scalar field will make what we call it reheating of the universe. Reheating of the universe. Okay, now what we are care about it at this point here, when we have the quantum fluctuations, and then from the quantum fluctuations we can describe what we call it, let's say, classical perturbations. This happens when the wavelength of the quantum fluctuations exceed the Hubble radius. When this happens, when the wave, or let's say here k, the wave number of the wavelength of the quantum fluctuation exceed the Hubble radius, then we have something, it's called the freezing of the mode. These quantum fluctuations will be freeze. As a result of this freezing, this quantum fluctuations, it's classical perturbations. Classical perturbations will be in the CMB, and then we can study this CMB, we can study these fluctuations in CMB, and then we can predict something about this inflation. Yeah. Just 1 second, I'm coming. Sorry for this interruption. Okay, so we're talking here. Now here about these perturbations, now there is a constant on this perturbation, that's the ratio between the amplitude of the scalar perturbations and the tensor perturbations, because in the case of perturbations we have more than one mode, should have a specific value less than 0.1. And we have about the scalar perturbations, we have the spectral index should be around 0.96. There is, of course, mathematical concept, and there is techniques about calculating them, but this is not our topic here and not our scope of behind this lecture. So this is not when we want talk about this one. And in addition to this, now the inflation, because the inflation initially is proposed, the idea of the inflation is proposed to solve some problems within the Big Bang theory. It's called sometimes as big bang puzzles. One of them is called the flatness problem, horizon problem, monopoles problem. Now, the inflation to solve these problems should satisfy that the number of e-folding should be between 50 to 60. What this number of e-folding? Let me remind it. Again, let's remember that the inflation, it means the accelerated expansion of the universe. So usually we say that's okay. It means that the scale factor of the universe at the beginning should magnify or should increase. So the scale factor at the end of the inflation should be magnifies with respect to the initial scale factor, and usually we take this as exponentially as n. So number of e-folds, number as a number of e-folds. So AF equals AI exponential to the bottom n, which were n the number. So according to that's the number of e-folds should be between 50 and 60, and there is one of the studies showed that's 25 n. If in even 25, that will be enough to solve the problems of the Big Bang theory. It means that the scale factor at the end of the inflation should equals to the scale factor at the beginning of inflation multiplied by e to the power 50 approximately. Okay. So this is the meaning of the number of e-folding. So here n in terms of the number of e-folding and r in terms of a number of e and the scalar tensor ratio in the number as the function of number of e-folding. All that I'm trying to show you here about how we can use this modified gravity in case of inflation. Now let's see that's not even here the Sterpensky model, and it's about the Sterpensky model and how we can deal with this one. Now from the beginning we can see that's okay. Look, now we have the Sterpensky model. It's equivalent to the scalar field inflation, because now we have here this scalar field and you have this auxiliary scalar field. It seems that we have scalar field inflation. In the section 2, they are talking about the Higgs inflation as one of these this declinant of Sterpensky model. So let's see how we can understand this. Higgs inflation, it means that now we would take the Higgs field as the inflaton. Look, sometimes we can, it's not necessary to say that it's exactly the Higgs one which will be taken as the inflaton. We can say that's okay. It's only similar to the Higgs, but if we added let me just talk about this one slowly. Okay, we have Higgs. I'm sure that all of you know what the Higgs field. Now the question was, can be the Higgs, because the Higgs is a scalar field. So can the Higgs, which after the spontaneous symmetry for breaking the interaction of the other fields with this Higgs within the Higgs mechanism, will give the masses for the other particles. Can this field play the role before the spontaneous symmetry of breaking? Can it play the role of the inflaton itself? Okay, when they studied the Higgs inflation, they found that no, it's because there is some concept. But actually, when they add something, it's called non-minimal coupling to gravity, they found that there is like this possibility. Maybe yes, it will play this role. Maybe will play this role. So here we can see that this is the Higgs inflation model. That we have Ricci, because to describe the gravity, we have here, this is the Higgs. It's complex scalar field. So we have nabla mu h, and we have h dagger. And here this is represent the potential of this one with the mu is the expectation value for the vacuum. Lambda just as coupling constant. And here we can see that's here. This is some kind, it's called as non-minimal coupling to gravity. It's as a result of the quantum gravity. We can find like these terms, where the xi h squared, h dagger h like h squared multiplied by r. So here they will try to show that this here, this scalar field model of inflation actually equivalent to Sterpensky model. Now let's remember that here, let's see what this, in the unitary gauge, where h equals h over the square root of t and h squared equals the larger than 0, the theory is described by this one. Now we have r, we have here 1 over 2 psi h squared r, and here we have lambda over 4 h squared, because we took h as larger than the expectation value of the vacuum, and this is all of this within the unitary gauge, where the Higgs mechanism is described by this one and by this real scalar field. Okay. Now in this case, the successful inflation exists for xi squared over lambda to the power 10 to the power 10. During inflation, the kinetic term is by definition smaller than any potential term. And this is what we were talking and mentioned about this one as a slope. Why this one? Because if this one is not, it's not working, or if the kinetic energy is larger than the potential, then we have positive pressure in this case, and we cannot find the equation of states to be suitable to produce accelerated expansion. Okay, so now according to this, that this term is smaller than this term, so we can cancel this term, and then the action of the Higgs will take this form. Now we have r 1 over 2 psi h squared r minus lambda over 4 h to the power 4. Immediately we can see that now we have here linear with respect to r, so we'll make that some transformation. But before that, we have h, it's a scalar field. So if we want to find the equation of motion for this scalar field by applying the Euler-Lagrange equations, we cancel the variation with respect to x. So all what we need is that the variation of this action with respect to the scalar field, that should be equal 0. Just let me clarify the idea clearly. Euler-Lagrange say that's nabla mu, and here you have the variation of s with respect to nabla mu h minus the variation of s over h, that's equal to 0. But this term, it's actually equal to 0 because we said that this term is smaller than the potential, so we cancel this term and we still have only this term. And if we took the variation of these two terms, which contain h with respect to the h, that will be psi hr minus lambda h to the power 3 equals 0. From this one, we can find that h squared equals psi r over lambda. Okay, so then what we have here, is that now the action of the Higgs will be written as m blank squared over 2r plus psi squared over 4 lambda squared r squared. So this is Sterpensky model. Therefore, during inflation, Higgs inflation is the Sterpensky model. One symbol has to undefined by m squared lambda over 3 psi squared. Since we know that m should be 10 to the power negative 5, that's from this one. We found this constraint. That's to achieve this result, m should be 10 to the power negative 5 from the normalization of CMP and isotropic. Then we can see that we get that psi should be 10 to the power 10 lambda, which is not surprisingly the value needed in Higgs inflation. In addition, the vacuum energy which derives the inflation is then should be given by this formula. Now, so this is about now by working on this one, we show that Higgs inflation is as you know. Honestly, I want to know how we can decadent. I think like this, decadent maybe. Let me pause the recording and I'll back. So descendant. So Higgs inflation as descendant of Sterpensky model. Now we have another thing, that's universal attractor models as descendant of Sterpensky model. Now there are generalize the idea here. It's not about only the Higgs mechanism. It's not merely as an accident. In fact, the Sterpensky model is also equivalent during inflation to the general form of non-minimal coupling proposed in reference 17. What the meaning of this? It means that if we have non-minimal coupling between the scalar field, if you have any model here, look, F5, if you have any model of scalar field, single scalar field inflation, it means that the scalar field he was responsible to drive the inflationary epoch of the universe. Then, in this case, any model of scalar field, canonical scalar field with potential, any potential natural inflation, chaotic inflation, exponential inflation, power law inflation, with non-minimal coupling between the scalar field and rich scalar, that will be equivalent to Sterpensky model. Let's see how this will be happens. So we have omega phi, look, it's omega squared. So omega squared means that's omega p, mb squared, I'm sorry, multiplied by r. That's Hilbert-Einstein part of the action. And then you have psi fr. This is non-minimal coupling to gravity. If we looked here as a non-minimal coupling in case of Higgs, that will be h squared, but here they wrote it in general case. But also here actually they put because we are talking about the attractor model. In case of attractor model, the Vj will be exactly like this. And also here they mentioned that it should be noted that this kind of models has been discussed in reference 2020, where it was pointed out that they are not technically natural, because as there is no obvious way, that's the symmetry, for example, to preserve the relation between the non-minimal coupling and the scalar potential, because here we have that the scalar potential should be like this non-minimal term to the power 2. So why do we have like this? It's so they consider it's not natural, but they studied this one, and here they are trying to show that this kind of potential, this kind of models equivalent to Sterpensky model. Now with the same, so here they wrote it, that's this one, 1 over 2 psi f phi r and here f phi. We may integrate out the scalar through the equation of motion. So if we took the equation of motion for phi, but now we have 1 over 2 psi r f prime, phi minus 2 f prime f with f. Just take the derivative with this action with respect to phi, and be careful that here there is no dependence on phi. And the scalar field equation admits two solutions. So the solution for this one is that f prime equals 0 or f equals 1 over 2 psi r. If we took 1 over f1 over 2 psi r, then f prime will be here. That will be 0, and here we have this. I'm sorry, not 0. 1 over 4 psi r. Yes, let's imagine that r is like phi. So with the derivative with respect, that will be 1 over 4 psi. So it will be 1 over 8 psi squared r. Let's just check this. Here we have negative 2 f prime. F prime, we say that's 1 over 4 psi. And here you have f. So f will be 1 over 4 psi r. So we have here, we said that here we have 1 over 2 with 1 over 4, so 1 over 8. And here we have 1 over 4 with 1 over 4, but that will be 1 over 16. How did they find that this is f equals 1 over 4 psi r? They solved this equation. It's not something difficult. So we can, let me just check. It's something easy. It's not difficult to check. So f prime, that will be 1 over 2 psi r minus 2f equals 0. So we need to solve this equation. So d phi, we have the first one that's f phi will equal 0. The second one that's f prime phi, say that's f prime phi, or f phi should 1 over 4, 1 over f, 1 over 4, let me check again, psi r, psi r. Yes. This one now. I'm sorry. From this one, even this equals 0, or this equals 0. If this one equals 0, so 1 over 2 psi r minus 2f. Yes, now equals 0. So f will be 1 over 4 psi r. Yeah, this is the case. I'm sorry. As I mentioned, I didn't go through the details. I'll just read the paper quickly, understand the main idea of the paper without going through the details. So yeah, this one, we have the another one. Now the equation 219 is solved by constant configuration, that's phi equals phi star. Therefore, it corresponds to Einstein gravity with a blank mass and cosmological constant. However, the second solution gives this one. Let's just understand what the meaning of each is. So if that's f prime equals 0, so if f prime equals 0, then f should be constant. F phi should be some constant here, and then actually here constant. So now we have here, like if we have coefficient, look what the meaning of this. If we say that's f prime equals 0, then f will be constant. Let's say that it's c. So what we have from here, we have m blank squared over 2, 1 plus 1 over 2 psi c multiplied by r minus c squared. Now we can see that this one, it seems as a cosmological constant. So this is the theory with cosmological constant. And also here we have effective max Planck, because blank mass, effective blank mass, because Planck's mass should be like this, and usually this constant multiplied by r. So this we can take it as effective mass, blank mass. So here they say that's it's equivalent to Einstein gravity with blank mass, this one. I call it C, they call it phi, f phi star, and cosmological constants as lambda squared f phi squared. I call it here, that's C. Now about the second equation, if we look at the second equation, so here we have f phi, and f phi is with r, and here we have, so what we have here is that we have r, and here we have another term with r, and here we have also another term with r squared. So just by taking f as 1 over 4 psi r, then we have what we have here. From this term we have 1 over 2 psi squared, okay, psi squared over 8, because we have 4 r squared, and from here we have psi squared r squared over 16. So that will be psi squared r squared over 16. Yes, plus, well, not minus, plus. So check, yes, psi squared r over 16 r squared. So this is again Sterpensky model. So Sterpensky model. So this class of models also equivalent to Sterpensky model. But now, in case of Sterpensky, this m squared will, it should be as 4 over 3 psi squared. And the vacuum energy that drives the inflation turns out to this form. It's that you see that's how we can find this one. How we can find that's the equivalence. Now here they say that's higher dimensional Sterpensky model. I will make mistake about the pronunciation of this word, so I will not say what this. I know what the meaning of this. I'm sure that most of the people who are following this lecture, they are better than me in English. And I cannot live without black tea. Okay. So let's discuss now higher dimensional generalization of Sterpensky model. Let's see what is. It means that now we have r to the power b, where r is 4 plus d dimensional rich scalar, m star is corresponding Planck's mass, and a and b are dimensionless parameters. The higher dimensional theory can be linearized in the scalar curvature as usual by introducing auxiliary field. By auxiliary field, we will define it by like this. So here we make the conformal transformation, and we define this auxiliary field. And omega is given by this. Here we have phi squared. Here before doing the just to linearized the action before the conformal transformation. Then after that we can make the conformal transformation, and now the conformal transformation will take this form. Just take m to the power d minus 2 over 2 out, and then you have here 1 plus 2 omega phi squared over m star d to the power minus 2 d minus 2. We may write the action, this action to how, where v, this is just another way of writing this action. Oh no, yes, now after the conformal transformation, the action will be written in this way. And we have nabla mu log f, where v is given by this formula. Clearly, in order to get Sterpensky-like model, we need that's d minus 2 equals to this. So if we put these constraints on the constants, on the constant parameters or dimensional parameters, we can recover Sterpensky model. And the action turns out to be, take this form, then by defining auxiliary field with respect to the log sigma, exactly as before, log omega, I'm sorry. Then we have this one. Now look, we have here r, and then we have auxiliary field, and here we have potential. After dimensional reduction in in d minus 4, we get a 4-dimensional action. So now we back to that 4-dimensional action after identifying this just as a definition, where Vd minus 4 is the volume of the Td minus 4. We assume, of course, that the torus moduli, or at least its volume moduli, are stabilized. The potential of this generalized Sterpensky model is of the general form. This is the form. And again, because now we have a clear case with Einstein gravity in addition to scalar field, this is studied, and the spectral index is given by this formula, and the scalar tensor ratio is given by this formula. Now we conclude this section. We conclude this section with comment on conformally invariant two fields model. Here they are talking about the two fields model. Then distinguishing Sterpensky model from its declinants. And let's say it's approximately reached to the half of this paper. So I will stop here. I will stop here for this lecture. I hope that I succeeded to clarify the idea. Inshallah, in the next lecture, I will go to the other of this paper and read it and give comments about it. But I hope that you found it interesting lecture. If you like theoretical physics, you should like it interesting because you learn something new now. Please, if you have any question about the details, don't hesitate to ask me about it. I have the enough experiences to do all of these calculations. It's not something difficult, but again, it's because the idea is not about the inflation itself. It's the idea about the FR theories and to see how these FR theories can work in case of inflationary epoch of the universe. Thank you so much for your listening. Have a nice day, and see you later.